Hello everyone, and welcome to this fourth lecture of this course. So I hope so it will be the last one. It might be getting more covered, but I hope to cover in 2 hours. Okay, so what I have here is just to recall the things which we have done in the previous lecture, right? And actually we have done these things in detail with the fine variety, and now I have just written these things with the quasi-projective varieties. Definition is little bit uh, extended because we have already seen in the projective case the usual definition of the regular one is not working because we have the examples whenever you have a regular function in the fine setup. It doesn't mean that in the projective setup you have just a single function or single polynomial which is for which the regular map can be defined. So that's why we need some open set, or you can say that we need locally to define these regular functions for the projective varieties, right? So that's also work for the quasi-projective variety. And what is quasi-projective variety? Quasi-projective variety is just the union of closed and open set of projective variety is so projective space is actually called the quasi-projective variety. And we have seen in the last lecture that every affine variety is actually a quasi-affine variety, and similarly every projective variety is also quasi-projective variety. Okay, so now I have defined this regular function, so I'm taking V and W my quasi-projective varieties. And then we have defined here what is the regular map. So for regular map, we just need to find for each V, as I said that we need to define this one locally. So for each point, there is always a Zariski open set which contains your of this D, and definitely a sequence of polynomials because regular maps usually are depending on polynomials. So we have chosen these polynomials, and you need to consider that they should have the same degree because we are working in the projective setup, so that's why we need this homogeneous part. And furthermore, the degree, uh, which satisfies these two conditions that for every u, sorry, every point in u, this is non-zero for all I, and furthermore, for every point in u, I of y is actually equal to written in this way. I mean, the image of this one is represented by this sequence of polynomials at that point, right? And definitely this point belongs to W, of course. Otherwise, it doesn't make any sense, right? Okay, so this is the definition of a regular. So you can see that what you are looking, it's similar like a regular map, which is defined by a sequence of polynomials, but now we are doing this one locally. I mean, for each point, you can find an open set for which this is true, and further, you can have these properties. Okay, one may ask this question, what about the intersection? Definitely on the intersection, they have the same answers. Whenever two different open sets have this non-empty intersection, they will satisfy those conditions of that one. Okay, now idea is to develop for the rational map. So for rational map, I have here some setup, right? So for example, these are just, you can say that some notation we need to define for the rational map. So I'm taking here x, which is consisting of n plus 1 tuple of polynomials, right? Which are homogeneous of the same degree, right? And furthermore, we are requiring that fi is not equal to 0 for all b. So we have considered some b, which is a quasi-projective variety for all I. And furthermore, so if you look these conditions, these are just following these regular properties. But there is another one which is hidden. So this collection of points, if you see that these are satisfying all this setup, which means that they are like behaving like and whenever you are picking a tuple, this is like a fine, sorry, is a regular function, behaving like a regular map through this B, which is sorry, A, which is equal to B, because it's satisfying the same conditions here. And now what we are doing So you are just considering here, let's say that you are considering all regular maps here somehow, right? I know you are defining this relation on this one, which is an equivalence relation. So how I have defined this equivalence relation? No, we are not calling these regular maps are local, but they are defined as locally. I mean, they are defined. You can say that locally these are polynomial maps, right? Like usual for a fine variety, right? But when you are looking, because if you remember the last example, we cannot define with a single set of polynomials for the whole thing. So that's why we have to define in the quotients. So that's why it is called locally. It's defined in a local way, right? So local trees are like polynomial maps.
Sorry, I missed one point. What are the open sets in Cauchy variety?
You know,
Cauchy projective variety.
because V is up here.
What are the open sets in Cauchy projective variety?
Is the same as whatever you are taking in your projective variety.
Okay.
I mean, no, V is actually a subspace of that one. It has also this is topology. So you are considering all open sets which are these key open sets of a subset of V. That is the definition. You have a big set, projective space, there is a topology, you have a smaller set V, there is a topology, and now you have an open set in your V. So definitely it satisfies that connection.
Okay, so it is induced topology.
Yes, it is. That's why we already said that every variety, every affine variety has a discrete topology. Affine or projective, whatever you are taking. Right? Okay, so now we have this, we are saying that these two things are equivalent if and only if there are corresponding projective points for every point at every point of B, they are equal. I mean, they are just giving you the same result, right? And you can see that this is same if and only if you want to calculate these functions on B, they satisfy this relation Fi times Gj is equal to Fj times is equal to Fj times Gi. So you can write this one in this way as well. Some sort of setup. But it is the same thing. So from here you can see that why it does make sense for the rational part. Okay, now it's time to define what is a rational. No, we have defined regular function local. I mean, so if you remember last time example, so let me just recall that example. So I think it would be clear for you to see that how it is working. So if I will go with this one, so if you remember this variety, so we have defined this map from B to P1. This is projective variety in this way. Okay. So I'm calling such map is actually a regular function, right? But if you will just see that one, you can ask this question that, but it is not like a polynomial map as we have seen in the fine variety case. So fine variety case, we said that it is defined in this way. For example, if we are considering this as project fine part, then we will say that this is just defined to some polynomial. So it's not this is for all x y belongs to your variety. If phi is a from some B to some, you can say that K1. right? So this is like, so every polynomial map is like a regular map, but here this is not a polynomial map. But locally it is polynomial. Right? So locally it is polynomial. So that's why we said that this is overall a regular map. Okay?
May I ask a question?
Yes.
For example, whatever you are saying is absolutely right in the present context of discussion. But for example, when we say a projective space can be seen as we studied or looked at yesterday, that it can be we can glue together affine patches or affine open sets that we called yesterday.
Yes.
And on each open set we have regular function. Therefore, on projective space, automatically we can translate these sort of regular functions to projective space. So,
That's true.
is okay? Is that right?
Yes, that's true.
Okay, okay. Thank you.
Because remember we defined that Pn as just a union of all ui's, right? So from here. So these are called affine patches or affine open cover for this projective variety. And if you want to work on all this P, then definitely you can work on these patches. And you have to work in these patches in such a way whenever they have non-empty intersection, the answer must be equal on every sector. Whenever it is that. It's same like you can imagine like if you have done the manifolds structure. So for manifolds you have some setup. The bachelor is satisfied certain conditions. So similarly, if someone has the idea of building manifold, so we have a similar kind of idea here. If you don't know what is a manifold, some of you, so don't worry about that one. You just consider here what we are doing. Okay. So now, what is a rational map? So rational map, of course, we have already seen it's not usually defined on whole V. So that's why we have this dotted line between as defined as a function from V to W. It's just an equivalence class which we have defined here. So if you will just pick not just a collection of polynomials from here, but you will are picking an equivalence class from here, then it is called a rational map. Right? And then we have a similar definition. A rational map is the regular at some point if we have these conditions, which means that they are non-zero. I mean, this must be satisfied because this 0, 0, 0 point is not any coordinate in the projective space. And furthermore, this belongs to this one. So this is the usual objection which we can raise here. So it's just depending on those points for which point we can find such kind of representation because this is just a class. So you have to choose your best representation for that one such that it satisfies this condition. So this then if you can find such thing, then definitely it's called a regular at that point. And the domain of the definition of phi is the set of all points where the phi is a regular one. So it's the same one that you have done in the affine case. Okay? I know this definition is again we have done previously. If you have two phi and psi maps, which are rational maps, and the question is, can you compose two different maps or not? Yes, you can compose if the image is dense in W. Because whenever the image is dense in W, then you know that the domain of the definition is always Zariski open set. And the open set, Zariski open set, when you are taking a Zariski open set in a irreducible varieties, because I am considering here that irreducible quasi-projective varieties. So whenever you are taking a Zariski open set in irreducible variety, it is always dense. So whenever you have two dense sets, their intersection must be non-empty. So that's why it makes sense that you can compose them. And such a map is called the dominant map, for which the image is dense in W. So if you have two phi and psi, two maps which are dominant, and this phi is called birational if they are inverses to each other, right? And there is very nice lemma. If you want to see that two irreducible quasi-projective varieties are birationally equivalent or not, then you can just see that are they have some open set B A in B and B in W. If they are isomorphic as quasi-projective variety, so you can extend that one to the whole variety. So you just need to see here everything on the open set. So you have two open sets in those two varieties which are isomorphic, birationally isomorphic, then definitely they are birational. Okay, now I will just give an example and then we will. Yeah. So my example is that, so you are very familiar with this variety, right? And this variety, Pn. So this is a fine variety, but it is projective variety, but they are actually birational equivalent because as a quasi-projective variety. So they are birational as quasi-projective variety. Right? So, and we know that there is a trivial map from Pn to Pn, which is defined as just the coordinates x1 up to xn, and which just projectiles and homogenize those coordinates, we get x naught, which is the mu variable. And by definition, it is a regular map, right? You can see the definition again, and you can see that these are just polynomials and polynomials, so that's why this is just a regular map here. Sorry, you don't need this one. I just want this one here because this is just like it's going in this way, right? Okay, I don't need to put any variable here. No, we need to define a map from Pn to Kn, right? So which means that we have these coordinates. And can you tell me any map if we can define in this way? Can you guess something?
Define it on
This
open.
point is in Pn, so at least one of the coordinates is non-zero,
Mhm.
so we can map the other coordinates to Kn.
Okay, so can we write in this way?
Yeah.
Okay. It's fine,
But
but what is the problem with that one?
it's just on user.
We should
It is
know
just
that
in
this
the
is
open
that
user.
X naught is non-zero.
Yes, x naught is not well defined on x naught, right? So this means that this is just working on use
Zero.
zero. Right? So because I just remember here, ui is defined in this way. Xi is non-zero, right? That is an open set. So this is well defined, but when x naught is not zero. So this works for. So this works only for Pn minus ui, u0, right? But still this is fine, this is a rational map. We don't care on which part is not defined, but on which part it is defined, that is perfectly fine, which is an open set. So the domain of this map, let's call it psi. This is let's call phi. So the domain of psi is nothing just V0. Okay? Which is an open the discrete set in that way. And now if you will just compose these two maps, you get the identity. This is phi psi and this is phi and that. Right? So this shows that K and these are birational equivalent to each other. So any variety, sorry. Birational means that they are not really isomorphic in a usual sense, which we have defined for the regular function. It's the same as birational means birational, not isomorphic, even in the quasi-projective space. Okay? But if they are coming from the regular parts, I mean, your function is regular one and the inverse map is also regular one, then they are isomorphic. But if they are working with the rational map, then you can't say they are isomorphic, then you will say that birational equal. And if there is some variety, sorry, yes.
We have that two affine varieties are equivalent or isomorphic actually. If their coordinates ring are isomorphic.
Yes, but here we cannot talk about their coordinate rings because we are working here in the quasi-projective part.
No, just
Okay, so
thinking of
an
analog.
yes.
Okay. Analog here. What is the analog for quasi-projective?
There is no such one.
Okay.
Whenever you have a quasi-projective variety, right? So if you remember what was the coordinate ring? Coordinate ring was a collection of all regular maps from V to K.
Yes.
Right?
Quotient of
yes. So in a similar manner, we can also define for the quasi-projective variety, but not in that sense, but through these maps. For example, regular. If I want to find a regular map on V as a quasi-projective variety, then definitely I will take a map from V to K. That is called regular on V. So if you will collect all those regular functions, then definitely it's called the corresponding coordinate ring of your quasi-projective variety.
Okay, thank
Sorry
you.
if I did
Yes.
something wrong before that. So yes, you are right. Whenever you have two varieties which are quasi-1, they are birationally equivalent. Then if and only if their corresponding varieties these are field of fractions because here I am considering irreducible one. They are absolute. Right? And what is this one? This is just collection of all rational maps from V to K. That is just a restriction, you just, sorry, K instead of K. Projective space. Okay, now it is clear. Yeah, any questions so far? Okay, if there is no question, so let's do a couple of more examples, right, which are very important ones, and then we will move to the graph matrices part. Okay, so for example, P and cross P and okay, that's very important here to describe that K and affine, if you are considering the affine spaces, and if you are taking the cross product of those affine spaces, they are, you know that this is isomorphic to K and plus one. Right? So that's why it is trivially an affine variety, because we have this isomorphism here. But we don't have any isomorphism here like that one. Or something here. Because we don't do it, right? Okay, so how do you see that this product, when you are taking a product that is also a projective variety, but we will see not directly P and cross P and, but we will see a certain image of this one in a new bigger variety, projective variety, and that is to become Segre variety. So I will define that one. So for example, this is defined in this way, and then so you have x naught, x n, and then you have coordinates y naught, y m, right? So you want to define here this map. So how we are defining? So I am defining a map from n to n is some big one. So can you just tell me how we can see this thing? I mean, any idea how we can find this one much bigger than that this one is lying in this projective space? I don't know. Any idea you can share with me? Do you have anything like that which you can say something? How can you find this thing?
We take a product of each coordinate.
Product of what?
Coordinate.
Of all coordinates?
Yes.
Okay, so this is one of the idea. Yes, we can take the all possible products corresponding to these coordinates. So I can just write this one in this way. So of course I cannot write all of them, but I can write in this way, which defines this one. Right? Agree? Or I can say this one is just like
This is the
okay. Like here, which means that you can just plug in the values and you will get the answer for that one. I mean, I can just define the coordinates if I'm saying that how many coordinates are there. So can you answer through this one? So it's like a matrix notation for you, and you can answer the how many coordinates are there. There are n plus 1 into n plus 1 coordinate. Right? And if you are taking this one as in a projective space, I mean as a homogeneous coordinate, so what will be this thing?
m into n.
N plus n, and that's it. Agree? You get that is m plus 1 into n plus 1. But in the projective space, with one coordinate is there is more than one coordinate as a dimension. Right? So let's see an example so I think a little bit more clearly. Okay, but here you can see that this one is a regular map. Agree? So this one is a regular map. Because everything is here polynomial here. So this is a regular map. The image of under this map, which is called the Segre embedding. Why it is called embedding? Because this is injective map. We can verify this one is an injective map, and this one, the image of this, sorry, this BMN, the image of this product is actually is a projective variety.
This is the injective map.
Sorry,
This is injective map.
it's an injective map. You can easily verify by definition. Okay, so let's start. If you have P1, and here is again P1, and what will the answer will be?
3,
Eh?
3,
3, because they say here 1, 1, 1, so it is 3. And how you are defining here?
This is a homomorphism in some category. Secondary embedding.
Sorry,
Secondary embedding is an homomorphism in any category.
just let me just complete this one, then I will answer your question. So I have written all possible products here. So you can see that when M or N is 1, 1, then you have this kind of map. Right? And if I will write this map in a more nicer way, then you can see that why it is called the projective variety. If I want to see that why this is called the projective variety, okay, let's take your question.
I was saying that this secondary embedding is an homomorphism in any category except
It's a regular map.
because I can see some more elements in kernel. So how it can be injected? Like if I take if I take 0, 1 and 1, 0. So its image will be
0, 1,
and
and
1,
1, 0. So what is the answer?
So
0,
it will
0, 0, 1.
yes, yes.
Okay. Okay. But if you look this one and to what we are saying that the image is actually a projective variety, so we can see that I can write this one in this form. Just imagine that. Right? And it is nothing, just I can write this one as a matrix form. No. Sorry. Right? And if you will just see this one as a matrix, so what is the rank of this matrix? What is the rank of this matrix? I think it's very easy to check that. What is the rank of this one? But it's difficult. You can take this one as a common here y0, and you can take here from y1, and you can see that both rows are equal. And because there is no 0 row at all, so definitely its rank is 1. So rank of this matrix. So this means that I can write my image under this map. It's nothing, just this one is the I mean I'm just using this notation Zij at this moment, just like I had used previously. So it's like a matrix, any matrix here, whose rank is 1. Right? So I can write here the image of this one as a matrix whose rank, because I can just write these coordinates which are written here, like here, just by my setting. that if I can write this one as a matrix in this form, then definitely I will choose that such points whose rank or such matrix whose rank is 1. Right? So this means that by definition it is a variety because rank, what is the rank? Rank is just a polynomial setup. I mean, how you will get something of the rank? Can you answer that question?
If it's rank is 1, then like minus of.
Because we have 2 by 2 matrices here.
So
So
minus
rank one means that is determinant is
0 or
I
minus.
think right here the determinant is 0. Because determinant, I can write here the determinant 0 because matrix cannot be equal to itself 0. Right? So I can just replace here that this is determinant of its matrix is 0. And determinant, you know that is just coming, just can be written as a polynomial function. So that's why this is a projective variety. But it is because 2 by 2 matrix, so it's easy to see that. But if you have n by n matrix, like in a general case, like here, and still it satisfies that this matrix must satisfy this condition that its rank must be 1, because it has similar kind of setup. If I will just write this matrix, then you can easily see that. Right? And from each part, I can just pick these variables, so it's equivalent to just a matrix whose rank is 1. So for more general setting, when your matrix has rank 1, what does it mean?
All minors.
All
minors are 0. Minors.
Minus of 2 by 2.
Yes, all matrices of order 2 by 2 or all minors of 2 by 2 matrix 2 by 2 setup, they are whose determinant 0. So this means that in generally, when you are talking about this image, so you are picking all those matrices such that whose all submatrix 2 by 2 submatrix have determinant 0. Right? So that's why it is a projective variety. Okay, that's it. This is important one to clarify, and this is known as Segre variety, right? Because it's a variety, so it's called a Segre variety. Okay, so if you have any question related to this projective variety, quasi-projective variety, or in this setup, please ask, because now I'm moving to totally different question, because we are now interested to how to conclude these things. Or I will write here few couple of questions and how we can answer those questions. So is there any questions so far? Okay, if there is no question, so let me just write a couple of questions. I think I have 3 questions here. The first, actually, the problem, ideal membership problem. So let me just write these problems, then we will try to solve these problems, right? And what are the methods? What can be the algorithm? Okay, the first thing which can be invariant is just
Field of friendship.
coordinate field of friction. Yes, if we are talking about the setup of bilateral, then definitely it's a field of friction. Otherwise, it's a generally coordinated. Actually, let me just add few words about the varieties, because here I didn't define very abstract varieties, but generally you can see that every variety has spectrum of its coordinate. Coordinate. Because spectrum means that you are collecting all maximal ideals in your coordinate ring, right? Every maximal ideal is corresponding a single point in its variety, so that's why we can write here this one. And this setup actually satisfies the discrete topology structure. And the other thing which we have, the collection of all regular functions on that one. So every variety, whenever you have a generally, let me just talk about generally. So it's very, they are very abstract things which need to be defined before defining the abstract variety. So every variety is basically basically depending on the regular function. So if you know the regular function setup, then you can talk about a lot about the variety. So in general sense, I can just give you some sort of example. You can say that. So if you have this thing, which is some topological space, so I'm talking about more general abstract variety. So I don't know anything about what is this topological space. And if you have these collection of all regular functions, because I didn't talk about much about what kind of the properties regular function setup can have, right? It satisfies certain conditions which are called shape. So I'm not talking about at this moment shape. So you have this x, you have this regular function on x, and then you call this one is an abstract variety if it satisfies certain condition. For every open set, you have the corresponding local regular maps, which are actually isomorphic to the affine variety. So that is more general definition of variety, right? So I'm not going in that detail at this moment. But now we are going to do some calculation to answer, because we have a lot of questions during these setup, like affine setup or projective setup, and we need to answer those questions. So for example, the very first question, because we know that so why affine varieties or projective varieties are important, because as I said that here, whenever you are considering abstract variety, locally it is just isomorphic to an affine variety. So that's why it is important to study these affine varieties better and projective varieties better. Okay, so then, okay, what is the ideal membership problem? So for example, you are given a polynomial, right? And you have an ideal. So how do you determine that this polynomial is a part of this one? Is there any algo? Right? So which says that polynomial is a part of this ideal or not? Right? That is the first question. Automatically we can see that this affine variety lies on this hypersurface or not. So automatically this is equivalent to this question, because this one is more than that one. Right? Okay, so this is the first question which we will try to answer in this part now. Another question, which is called the problem of solving polynomial equation. I mean, you want to know what is your affine variety. Or right? You want to know how you can describe this one. So this means that you know that what does it mean? It means that this is a solution set. Simultaneously, you have to solve those equations. So how you can solve those one? And the third very important one is that it's called utilization of utilization of. So for example, so let me just describe here. Let be given by. So you have a set here at this moment which is given by parametrically. X1 coordinate is given by this function, and similarly x and n coordinate is given by this function in these variables t1 up to tn. These are different ones. Here GIs can be polynomial or rational function. Right, in TJS. So if you have this kind of set, then this definitely this V is actually an affine variety or a part of an affine variety. So the question is, if you are given such data, so can you find polynomials which defines this variety or a part of this or some part of some variety, right? So you need to find these polynomials. I mean, you need to find these things actually. The question is that one. So I know that this is some sort of a variety, but what are these at first? So this is something unknown at this moment. So these are three major problems, and to answer this question, we have just one method which answers all these questions, right? And before that one, let's see what is this one, polynomial ring. So if you will consider just the polynomial ring in one variable, and we know a lot about this polynomial ring. We know that this is UFD, which means that unique factorization domain. We know that this is PID, principal ideal domain, which means every ideal is just generated by a single element. And what more we know about it? We know about the Devian algorithm in that case, right? So we know a lot about that one. So many of you are taking an ideal here. I know that this ideal is always generated by some polynomial. And if you have some element in your ring, then I can easily see that if I want to check that this F belongs to I or not, then what I will do? What I will do? I will use my Green algorithm. I will divide G by this F and I will get some quotient and some remainder, where remainder is equal to 0 or the degree of remainder is strictly less than the degree of F. G. F. 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 Okay. So now I can answer this question. This F belongs to I or not, because I know that every element of I which is generated by G can be written in this way. It's multiple of G. So this means that F belongs to I if and only if R must be equal to 0. So it's very simple to answer in this case. QG क्यों आएगा?
Because
We should divide.
she always
Okay.
minimum degree.
Because we want this thing.
G should divide.
Oh, sorry.
Should never be close.
Okay, I'm sorry. F should be written in this way. Okay, thank you. Thank you for that.
G.
Okay, right. Yeah. Because F is written in this way, and definitely if I is 0, this means that F is a multiple of G, then definitely You just need to check that the remainder is 0 or not. So it's very easy to answer in this case. And if you remember, okay, but one variable, it's not very easy to answer that question because there are a lot of other things which we need to fix at that moment. Because here we are working with just single variable, so everything is very well defined because we know that what is the degree of this polynomial that is just depending on. We know that there is a unique one, which in which way we can define. But if you have a polynomial in two variables, for example, this one, you know the degree is 2. This polynomial has degree 2, not necessarily to be homogeneous, but I had some other terms here. So I know that the degree of this polynomial is 2. But if you want to do some calculation, if you remember the Debye algorithm, there is very special setup. You need to divide or you need to subtract some special constant in that one. If you remember how you can derive that one. I'm not recalling that one, but you know that if you will do this one, how you get this thing. So, for example, this has some f is equal to this one. I'm not writing the rest of the element, and g is this one. How do I get this r here? To get the degree must be less than this one. So I'm assuming here my n is bigger than n, right? So I know that one factor here which I will use, that is this one g minus gn over fm xn minus m f. If you look this expression, I know that I will get a polynomial which is strictly less than whose degree is strictly less than the degree of n. Because here what okay, in this expression what I will get? This expression will be cancelled with this one. And you will cancel this one and you will left something which is definitely has some degree less than n. But if I want to do this kind of thing in this way, so what will be my first expression? Can I use this one? Can I use this one or this one? So I have various options for there. So I need to fix here something. And usually these are called here the leading terms, which are the corresponding your degree or the degree term. But here, what is the leading term? If I want to see that one. At this moment, I don't know anything. Okay. So what I need to do that on the very first step in the polynomial, more than one variable, I need to define some monomial ordering. Because here I don't need to define any ordering because I know that this ordering here in this case. 1 is less than x squared, and so on. Because there is no other kind of polynomial here. So I can just take this order and I can just define all the setup. But the question is, what about these monomials? Do I have this setup or not? Or what will be the ordering between that? I don't know at this moment. So this means that first of all, we need to fix this ordering. So we need to define this ordering on our polynomial group, and then we can talk about further. Okay, so let's define this one. So, well, okay, now I'm talking about in this polynomial name. So every polynomial in this case, for example, that is written in this term, at alpha, right? So this means that it's written in one x1, alpha 1, xn, alpha n. And this alpha is just like alpha 1, alpha n belongs to this V and greater equal to C. Right? So this is the notation for the monomial, which we are using here. And but I got one more notation that is this notation which is nothing will be right? Now I will find what is monomial ordering. So a monomial ordering is the relation on this polynomial ring is a relation. We will write in this way that relation will satisfy certain condition of four. First of all, it must be a total order, which means that any two, if you want to take any two monomials, they must have some relation. Total order ordering that. Is that total order? And the second thing is that for any gamma, alpha, beta, implies that. And the third one is that any non-empty non-empty subset as a model is well ordering property. So here alpha means that I'm just writing this monomial actually. I'm just rephrasing the I mean I'm just using this notation. Right? Okay. So now you need to set that on what kind of monomial you can use here, monomial ordering you can use here. So there are three classical monomial orders which usually are used in most of these computation. These are called lexicographic order, graded lexicographic order, and the graded reverse lexicographic order. So let me just say a few words about those one. Lexico. So I will just write it again. If leftmost non-zero of alpha minus beta is possible. For example, if you have here 1, 2, 3, and their correspond, okay, I'll write it later on. Beta is like 1, 2, 3. So you can answer this question, what is bigger one and which one is not bigger, right? So you just need to check alpha minus beta, and if you check alpha minus beta, that is 0, -1, and -3. But beta minus alpha has this positive entry, so this means that I have this condition here. This means that the corresponding monomial that x1, x2, x3 here is smaller than x1, x2, 2, and x3, 3. Yeah. Right, so this monomial is lexicographic order. So we use this relation for that. Okay, so for the lexicographic order. If so you need to check their monomial degree. If they are same, if they're bigger, then you will say that definitely that is bigger one. Otherwise, If this is the case, then we need to check that this another condition which satisfies this, which is written here, leftmost non-zero entry. Of alpha minus beta is positive. Which means that first of all, you need to check this graded component, I mean just the degree of the monomial. And if that is which one is the bigger, that will be the bigger monomial. Otherwise, you need to check the lexicographic one. And the third one is graded reverse lexicographic order. Here you also have the similar one. Okay, graded reverse lexicographic. Okay, here you need to check not from the leftmost, but you will check the rightmost non-zero entry of alpha minus beta is negative. Right? So let's see more examples here. So let's consider this XYZ. And here you can see that this is true because this is 1 0 0, this is 0 1 0, and this is 0 0 1. So by lexicographic order, they are in this relation. Okay, you can verify. Okay, this is graded reverse lexicographic order. I mean, graded as well lexicographic, but with the reverse connection, because I am using here rightmost non-zero entity of alpha minus beta is negative, so that's why it's called the reverse part. Okay, so this is by lex, this is true, and if you are checking this one, so you can see that because it's starting with x and there is no x at that moment, so this is by lexicographic order is always bigger than that one. So you can see that in lexicographic order, you can see that 1 is bigger than x, okay, x power, you can say whatever, 2, 3, no, here. So these are all bigger elements, and then you have here y. Right, and then the other monomials in terms of y. And then, of course, if you have something like xy, then definitely that is bigger than y as well. So whenever the monomial contains here x variable, then definitely that is bigger than the other monomial which does not contain any x variable, right? And let me just write here one more or two more. So here you can see that I have here x1 and this is 0, 1, 2. And by the grading, I'm not looking here just graded lex because its degree is more than that one. So by the graded lexicographic order is bigger than this one. And the last one is x here. So here, first of all, you can see that it's 10 is also 10. So the monomial orders degrees are same. So now let's see in which order I have written this one. This is 2, this is 3. So it means that is not lexicographic order as well, right? Not graded one. What about this one? Graded reverse or not? So you have started from the leftmost 2 minus 1, right?
Okay, graded lex, not reverse. It's simple lex.
Sorry, let me just. Yeah, it's 2.
Because we have two less
Yeah,
than three.
it's 2, not this 1 minus 2. So that's why this is graded reverse lex. Okay. GRL. Okay, so this means that whenever you have two monomials, you can just need to see that which ordering first of all you are considering and fixing first of all that monomial ordering, one of these three, and then you have need to work further. Okay. This is most important to fix some ordering before starting any work. Okay, now we have this thing, and now we can fix one term from our polynomial, which is called the leading term. So such term, if you have some fixed some ordering there, then we can always choose this, the one term which is called the leading monomial. Right? So I have few.
Can we have break of 10 minutes? Just for you. Just.
You have or me have?
You have.
I don't need.
Seriously?
Yes. Okay, we may ask from the online audience, do you need a 10-minute break or like 5-minute break?
What they're doing.
Yes. Any other one?
We need three more. Yes, ma'am.
Okay, sure. So let's have our okay. So in the break, I have just written few notations and some result. And definitely that's not important to look or read this one at this moment. Because we just do an example and let's see how it works. It's usual division algorithm, but it's multivariate polynomial division algorithm. So first of all, let's start with your polynomial ring. And you need to fix the ordering, like lexical ordering, graded lexicographic ordering, or graded reverse lexicographic ordering. So what does it mean if you are having a polynomial? And you know that the polynomial just is a collection of all monomials with coefficients in your K, and the linear combination of monomials. So what is the leading coefficient? So this is leading term. So LT means that it is leading term. It means that it is consisting of the coefficient plus the monomial F1, which is the biggest monomial such that the corresponding coefficient is 1. Right? Like in when we define degree, so we need to see that what is the degree of that polynomial, then definitely we see that the corresponding coefficient must be non-zero, otherwise it can have any degree. And so this is leading monomial, which means we will just write the monomial in that case, and leading coefficient means that we will just write the leading coefficient, which is here, which is here. Okay, there is one more property, leading term of the product is always the product of the leading term because we are working in the integral domain because our K polynomial ring is an integral domain. So that's why this is true. Okay, what is this division algorithm? So it's usual, you know that what we need to do in the division algorithm when we are just working with and with one variable, like the usual division we are doing for the integers. So, but here a little bit different because we are considering this set here, right? And we are taking any polynomial here. This set is fixed with some order. So we have picked this order in this way that this is ordered by the indices. So F1 means that is the biggest one, F2 is the smaller, and so on, so on, right? I know what you have to do. Whenever you are taking any polynomial, then you can always write this polynomial as a sum of these given polynomials plus something else. And these are also polynomials here, like in the division algorithm, right? Then we start just with the single element here, but now we have lot of elements here. Okay, what are the condition on this one? These I mean these terms can be equal to 0, or the leading monomial of f is always bigger than the leading monomial of each polynomial here. The first condition, and the second condition, this R, which usually will call the remainder one, it is either 0, or if it is non-zero, then no monomial in R is divisible by any leading monomial of Fi. This is very important, right? So, okay, don't worry if you don't need to remember that one. Let's see this example. So I have here two polynomials, F1 and F2, and the F is I chosen this polynomial, and we are working here the lexicographic ordering, right? So what you can see that with that one. What is the leading monomial, leading term of F? You can just pick those ones here, right?
Ordering between the variables, which one is bigger?
Sorry?
Ordering between the variables, x is greater than y is greater than.
Yes, this is X is greater than Y. Because it is lexicographic, so X is always greater than Y. Okay, in all ordering, X is, if you have this order, then X is always greater than Y, and Y is always greater than Z. Right? Okay, so here you can see that this is the one, and this underline, and it is very easy to see in this particular example. Now, but it is important here, as I said, that whatever I'm choosing my set F1 and F2, its order does matter in your computation here. So if you want to write, if you want to divide first this one, I mean you are giving the preference this polynomial, so then you can write your F in this way. So I'm just copying my answers at this moment. Okay, and if you want to say that how one can compute any two polynomials, then let me just write this method here. So this is F1. So you can do by yourself. Here I will write A1 and A2, which are the mutual quotient corresponding, and this is my polynomial. So look, it's leading coefficient, and now you will not look the coefficient, leading coefficient of F2, but you will give the preference first of all F1. So you will multiply this one y, so you will get xy squared, and then plus y, so you get that. So again, this is the leading term, because this is smaller than that one, so this means that it does not involve anything here, and it is again bigger than or smaller than.
We can multiply.
Yeah, we cannot do that thing, so definitely this will be 0, so we have this answer. And now, if I will give the first preference, to F2, then answer is different. So you can see that it's not. Okay, so if I will give the other preference, then definitely is X F2 plus 0 F1 plus 0 here. You can easily see from here as well. So this means that if I will answer this question, F belongs to this ideal which is generated by F1 and F2. This is true. But it is not given through this division algorithm, because in this division algorithm, this R is not unique, because it will just change the order between the given set of polynomials, then you will get some different result. So whenever R is 0, then definitely you will say that this belongs to this one. And if you are not getting R is equal to not 0, then you are not saying that doesn't belong to that one. So the converse is not true. So this means that this is helping. I mean, this ordering is helping, but it's not giving very nice setup. So this means that we need a very good set of polynomials which actually generate our ideal In such a way, we don't have any such kind of problem here, which is appearing at this moment here. So that such good set is called the Grobner basis of your ideal. If you are given any ideal and this is a set of polynomials in your I is called the Grobner basis if it satisfies this condition, which means that if you have the leading terms of all this set with all polynomials in your set G and you are generating this one and on the other side you have all leading terms of the I, which means that every polynomial in I you are taking the leading term from that one. And you are taking the generating, ideal. So you can see that these are monomial ideals actually. And if this is true, then we will call this one a Grobner basis. And now if you will work with Grobner basis, then you will not have such kind of problems here. Right? And when we ask that, do we have a Grobner basis for each I? So yes, answer is yes. Every ideal has a Grobner basis, right? But I'm not talking about that one. So if you have a Grobner basis, now what can do with the Grobner basis? So if you have a Grobner basis, then if you want to take k from that one, the polynomial from the ring, and you will just do this division algorithm now. So what you will get? You will get here something kn plus r. But in this case, this r will be unique one. And whatever the ordering you are choosing here, it doesn't matter at this moment. When you are picking, these one are the Grobner basis of some polynomial. Right? And this R in that case is written as F is divisible by this G set. Right? F is divisible by this G set, so this remainder is called that one. So this means that F belongs to I if and only if this is 0. So if you know that now what is the Grobner basis of I, you can solve this membership problem. So the first problem is solved in this way. Okay, now the question is how you can find this Grobner basis. Is there any criteria or method or algorithm from where we can find or we can develop this Grobner basis? So answer is yes, we have this one, and that is called the Buchberger algorithm. So I will just write that algorithm. So for that one, I need to define few notations. And then I can just define what is that algorithm, and I will explain through the example.
And what is this notation? R is equal to?
This one,
Yes.
F bar and G. This means that F is divisible by G. And whatever the remainder, that is actually the remainder when F is divisible by G. Okay, so let me just pick. Now I'm choosing, so let's define few notations to explain what is the algo. So set leading term of F is P x alpha, leading term of G is B x beta, and the LCM of x alpha, these monomials are x LCM. Is you know that what is the LCM? You will just take the corresponding maximum of alpha and beta, right? And now we have this CGZ, pair, which is defined in this way. X gamma, which is this LCM of x alpha and x beta, leading term of F times F minus x gamma over this thing. Right? CZG. Oh, sorry. CZG. Yes. Okay, so if you have this CCG pair, then we can easily check that through this one, that the given set is a Grubner basis or not. First of all, we will answer that question. So, for example, you have this set. And definitely I is generated by this set. First of all, it must be a generator of that ideal. So G is Grubner basis. Of I, if and only if this CCG of Gij must be equal to, sorry, the remainder of this CCG pair must be 0 when you are dividing by this G for all Ij. Of course, definitely. Okay. So this is the criteria. You need to check whether your given generating set is Grubner basis or not. You just need to check their all possible CCG pairs. And if their remainder by this given set is 0, then definitely it is a Grubner basis. So let's take an example. So I have example in 3 variables, y, x, y, z, right? And I'm taking lexicographic order with this order. Y is bigger than z is bigger than x. So I'm taking my order in this way. I mean, the first coordinate is corresponding to y, second coordinate corresponding to z, and third coordinate corresponding to x. So if I will use these two things, then I can just okay. So the question is, this given generating set is a Grubner basis or not? So what you need to do, you just need to calculate this pair, CCG pair, and what is that one? So I will just underline what is y is here and here is z. These are the leading term of the corresponding polynomial. I have just underlined those one, and if you will just calculate, so their LCM is xy, oh sorry, yz, and you will divide by y and multiply it by y minus z square, right? And similarly, you will minus this one LCM with this leading term, multiply by with this one. And what you will get this thing, minus bx squared plus yx cubed. Okay. So now you need to check, you need to apply the division algorithm. And by division algorithm, you can easily, after the computation, you can see that this can be written in this way, x cubed y minus z squared minus x squared z minus x cubed. Let me see, it was fine.
Y minus.
Okay, let me check again. There is some mistake in the calculation. This definitely this term will be cancelled out. The leading term from both terms will be cancelled out, and then you will have minus the cube. Okay, sorry. This is the Q. Okay. So now I just need to correct that one. Okay, let me check this one as well. YZ, oh, sorry, YX cube. Okay, that's perfectly fine now. Now I just need to write in terms of x cube, y minus z squared, and no z minus x cube, which is z squared. Okay, that's settled now. Now, so now you can see that when I have divided this one by these two polynomials, given polynomials, what is the remainder? Remainder is 0. So this means that this is actually a Grobner basis. Okay. So the remainder is 0. So this means that this, how I write, let's call it F and G at this moment. And this is nothing but 0. So this implies that G is Grobner basis. Right? Okay. Now the question is that if you don't have, what you will do if this CZG will be not 0 after the dividing by G. So what you will do? So the Buchberger algorithm says that whenever you have such CGP pair which is not giving you the remainder 0, you will just add this one in your Grobner basis. I mean, sorry, in not Grobner basis, in your generating set. So then you will do this calculation again for each pair. Whenever the pair it doesn't give you any 0, the remainder 0, then you will add it and you will add that one in your generating set. In this way, this process definitely will be stopped after a finite many steps, because this is by the Buchberger algorithm, which he has proved that it will stop after a finite many steps. So that's why you will get at the end a set for which every CZG pair is giving you the remainder 0. So that's why that becomes a Grobner basis. Okay, so let me just give what I have explained. I will explain this one by an example. It will be more clear to you. Okay, so let me just go with the example. Okay. It will be better to do this example. So now I have I. So x squared minus y squared, xy minus 1. This is, let's call f1. This is f2. Okay, now let's check this is a Grobner basis or not. So what we will do, we will just calculate this CZG here. And you know that this is, okay, I'm choosing here lexicographic order and I'm choosing this one. So I know that this is my leading terms into those monomials. So after this calculation, I'm not showing at this moment calculation, but let's do it in the first step. So the LCM will be x squared y, x squared minus y squared minus x squared y over xy minus. And you can, I guess, you can see that why we have used these kind of monomials and subtraction, because it kills the leading terms in both polynomials, right? So it's killing the leading terms, and what is left here is y minus x cubed. Okay. Now what we will do, we will check that one after the division of this one, it gives you the remainder 0 or not. So let's see that one. So now let's apply the linear algorithm. Okay. So you can see that if you will check that one, this does not give you any 0, because its leading term is this one. So this is the remainder actually. Because here, this is R actually, remainder which is non-zero. So this says that the CZG of this one after dividing with this my setup F1 and 2 is not 0. So what I will do, I will call this one F3 and I will add here in the generating set. So now my generating set is this one, F1, F2, F3. Right? Now it will increase your generating set definitely. Now what you will do again. Now if you will do this for the first pair, definitely this is remainder. It's not now cannot be equal to non-zero because it will be 0 because R whatever you have taken here that is actually the part of your new setup because now you will divide with F1, F2 and F3. So this CZG will add it in this one. Okay. And now you can see that F1 and F3, you don't need to check F1 and F2 at this moment. You will go with F1 and F3 and F2 and F3. Right? So if you will go with this one and you will get this thing. And when you will do this, apply this algo with this F1, F2 and F3. With 3 polynomials, it gives you 0. I'm not writing what is the answer, but I'm writing, what are the calculations, but I'm writing that is 0. And now you need to check, okay, this is fine for this one, but we need to check for F2, F3. And it is giving you y power 4 minus 1. And then you will check the remainder of this polynomial by your given set F1, F2 and F3, this will not equal to 0. And now what you will do, you will add this one in your set and now your set is becoming F1, F2 and F3. And now you have to check again all the setup. Now it will work for F1, F2, F1 and 3, 2 and 3, but now you need to check with all with these one. So, but here you can see that, I mean, you can check by yourself, this will be actually giving you 0 for all. 1. So now it becomes your Grubner basis, right? So we started with a generating set which was not Grubner basis, but we added more generators in that one to be a Grubner basis, right? Okay, any question? Okay, there is an algo in which you can see that how you can just work with this Grubner basis. Sometimes you need to do by hand at the beginning when you are a beginner, but later on you can just use the computer algebra to solve this one. Okay, you can share that one. Yeah. Okay, at this moment, let me just remark few things that Grubner basis is not unique. I mean, whatever you are getting a Grubner basis, so it is not unique one, right? But if it satisfies certain condition, which is called the minimal one, and the second is the reduced one, then definitely it is a unique one. So I'm not giving those definitions at this moment. I'm just going back to my questions, problems, which I already posed, that how we can use the Grubner basis to answer these questions. So I'm skipping those definitions at this moment. Okay, so far any question? If you have any question, if something is not clear during this calculation or something like that.
And sorry,
Sorry,
does this algorithm work with any type of order?
Yes. Any monomial ordering you are choosing?
No, any order that we choose.
Yeah.
If it's lexicographic or gradual.
I mean, definitely Grubner basis is depending on the ordering.
Yeah.
If you will change your order, definitely the Grubner basis will be changed. Because this definition is all depending on what are the leading terms of your polynomials. So if you have changed your ordering, so the leading terms will be changed. So answer will be changed. But these three are the most common or most workable monomial orders which are used in computer algebra, because from the computer algebra it says that these are the most. Okay, there is a link you can see in the chat box where you can use this online software for the computing of the Grubner basis. We call it 2, right? Okay, if there is no question, so let me just go with these problems. So I think so we have answered the first problem, the membership problem, because it's solved directly by the Grubner basis. So if you want to see that, if you are given a polynomial, a polynomial and an ideal, and you know that if you know that the Grubner basis of your ideal, so you will just calculate, you will just apply the division algorithm, and you can see that if the remainder is 0, then your polynomial is a part of your ideal, otherwise it is not. So it's very easy or direct way to check that one by using the Grubner basis. Okay, now Grubner basis, how Grubner basis can help to solve this second problem, problem of solving polynomial equations. So how you can do that one? So let's consider, so I will just explain these steps by examples, right? So let's consider this problem. I mean, you have to solve these equations. X squared plus y squared plus b squared is equal to 1. X squared plus b squared is equal to y. X is equal to c. Right? Of course, you have to solve in K3, which is actually C3. Okay. So now what you will do, you will consider your ideal, which is generated by these polynomials. So I can write all these one in a polynomial setup. -1, -y, and x minus c. Now you can see that if I will take the variety corresponding this I, it gives you the solution set of this collection of equations. Okay. Now what I will do, I will calculate the Grubner basis of this ideal, which I am skipping at this moment, but I am just writing the Grubner basis, right? And I will use here the reduced Grubner basis of I. With respect to, you can check later by might be you can use this online software to check that it is true or not. So I'm using the lexicographic order with respect to this ordering between x, y, z, and now what I will do, I will just write the Grubner basis. So I have 3 here, and this is reduced Grubner basis. So this is x minus c, g2 is y minus 2c squared. Okay. Now to solve this one is equivalent to solve these equations. Equal to 0. Equal to 0. And now you can see that more interestingly that if you look the last one, there is just one variable is involved. So you can easily solve this is like just polynomial in one variable, and you can solve that one. So whenever you will solve this one, and it is more easy because it's a quadratic, it can be quadratic if you will just replace d square by some other variable. So it gives you actually 4 solutions. And what are those 4 solutions? Let me just write those one. And if you can see that, you can easily also verify this one. Okay, these are 4 solutions. Now what you will do with these 4 solutions, you will substitute these 4 solutions here, and what you will get answer of this one as solve with respect to y. So this gives you actually y is equal to 2z squared. So this gives you the answer of y, and when you will go further, it's like just you are doing what is called in a linear algebra.
Backward substitution.
Backward substitution, yes, that is called a backward substitution. So you get this one x, y, sorry, y is 2z square, x is z, and z is itself here. So this is my solution set, and each has these 4 values here. So this means that this variety has only 4 values, right? So this variety has only 4 values, and now you can see that we have just used the Grobner basis, and we can easily solve this system of equations, which seems difficult at the beginning, but by the Grobner basis, it is quite easy. Okay, any question? Now let's move to the last problem, in which I said that if you have such kind of parametric equation, and now you want to just write the implicit polynomials for your variety. So how you can do that one? So let me just write this as a procedural thing. Okay, let me just go through the again examples. So let's suppose you are given V with these equations. At this moment, I'm just taking the polynomial, not the rational one. But you can take also the rational one. They are work, because when you will take the rational, you can make this one as a polynomial again. So now what I will do, I will consider my ideal. What is my ideal? X minus t 4, y minus t 4, q, z minus t. Okay. What is our target? Our target is to find such polynomial which are not involve any t, right? So how we can eliminate t from that one? So for that one, we need to fix ordering here of these variables x, y, z, and t, and then we can work with that one. So we will start with this ordering. T is bigger than x, y, and z.
This is the answer for the last question.
Sorry?
This is the answer for the last question.
Yes, is the last one. Implicitization problem. Okay, so if you will, I will choose this one and some, of course, lexicographic order. And what I will do, I will calculate the Grobner basis for that one. So what I will get this one. Okay, so for this ideal, I have calculated the Grobner basis. This one, I know what will be the answer of my variety. So if this is the variety, so variety is actually given in this way: P4, P2, P square, and P k. So can you guess what will be that one? I mean, what are my polynomials which are defining this variety? Can you guess? You will just omit these polynomial which involves t, and just consider all polynomials which don't have any t. So these are the implicit polynomials which we were looking for. Okay. So the Grobner basis also solves this problem for us, that you can answer such kind of questions as well to find the implicitization of your variety. I mean, the polynomial for which you are given by this setup. Okay, any question? There are lot of Grobner application of Grobner basis, but I have just focused with those problems which are very linked with this setup which we are talking about at this moment.
In the second question, which is always true that one of the Grobner basis will contain only one
Yes.
variable.
Here, it is not necessary to be true. But you can see that one thing in the Grobner basis list, there is one point of, I mean, you can always have least number of variables involved in your Grobner basis part.
So it's not necessary.
Huh?
It's not necessary to have one polynomial.
Yeah,
in one
it's not
variable.
necessary.
Same is the case with the third. one.
Because this is just, is the reason of this one because this is just zero dimensional variety. So that's why you are getting that one. Because whenever you have a zero dimensional variety, it gives you like just a finite number of points. Like, right? So finite number of points you can get only when you have there is involved one polynomial in one variable. So if it's not the case, definitely you can never have.
Same is the case with the third one, who will always get
Yes, you can always have such kind of polynomials which does not involve p. Because I have chosen t is the biggest one. You can omit because in the reduced, okay, I didn't say about the reduced terminal basis. In the reduced terminal basis, you can do that one.
What?
Okay, in the reduced terminal basis, you can always omit all those terms which are not appearing as a leading terms of the other part. I mean, the rest of the Grobner basis members.
Linear combination of other.
Not linear, exactly a term. I mean, might be possible you have that something here plus y here. But y is appearing here, so you cannot choose y here in a reduced Grobner basis. So you have to, you can, revise or you can refine like your Grobner basis in such a way. Always. There are a lot of other properties because I didn't talk about those ones. So definitely you have such kind of questions. So every time you can get such kind of setup or not. So general answer is yes. To answer such kind of question, we can use these reduced Grobner basis. Okay, any question from the audience? Okay, so far, let me just say a few words about the toric varieties. I didn't say anything about the toric variety because there are a lot of ways to define the toric variety. But here I can just give you a simple example of how we can say that what is the toric variety through these ideas. So I have already talked about the fountain idea, which is distributed by all polynomials. Like this one. Right? So these polynomials, sorry, this binomials. And now I can say that variety is called a toric variety. At this moment, I can give this simple definition, but definitely there is lot of data associated with that one, which we will see in the next week, right? So this is called toric variety. Just in as a language of algebraic language. So any ideal which is related by binomials that the corresponding variety is called the toric variety. That is the simplest definition at this moment. So any question? So is there any question from the audience? If you have, and then just mute, unmute yourself and you can ask the question.
Why do we need to give this variety a specific name?
Sorry?
Why do we need to give this kind of variety a specific name, like simple variety?
But there are a lot of reasons. I have just defined in the way which you have already seen. But there is a lot of structure. If I will just write the exact definition, you will see that there is more than. Okay, toric means that. So toric, say what is in your mind? Torus. So you can't see it as torus at this moment, but actually it is a variety which contains torus. And you know that there is an action of the torus on itself, which can be extended to the variety. That is the definition of toric variety. Which directly, if you will see directly this one, there is nothing at all like that one. But definitely that one was not like seven. Okay, so if you want, I can give you one more example. In that case,
What is stylish P?
Yeah.
Question, what is stylish P?
what is stylish P? Where is stylish P? Where is stylish P?
Predictive space.
Could you please ask where I have used at this moment? I didn't use any stylish P. And you know what is the total? Oh, it's stylish P is the projective space. If you're talking about that is the projective space. That is the notation from the projective space. Okay, if you want to know more about the toric variety, then I can give you like 10 to 15 minutes on that one, or I'll just give you some examples so you can see that how it is going on. If you want, then definitely I will do, and it's depending on the audience.
Yes, please.
If they don't want.
Comfortable.
Okay.
Recording of the.
No.
Okay, let me just ask if there are some questions. If there are any question, okay, Abdul Razik, I will explain you. Let me just ask what are the questions from the other participants, if there are. So is there any question related to this part which we have discussed today? Okay, if there is no question, so I will thank you all again for participating in these lectures. So hope to see you next week in person, most of you, or maybe someone are online, right? So if you have any questions, definitely I will be there to answer your question. Thank you so much. Thank you so much for joining and making it live. Thank you for my in-person audience. Thank you. Okay. Question now.
What do you mean?